July 27, 1944, Sandilagast, Normandy. The 88mm shell punched through the Sherman's hull with metallic precision that should have meant instantaneous death for 5 crew members. The Panther gunner from the 2nd SS Panzer Division watched through his sight for the eruption of flames that always followed successful penetration. Nothing came. The Sherman's turret traversed toward him, seeking targets. The loader froze in confusion. Every training manual, every combat report from Russia to Africa, every piece of intelligence confirmed that penetrating hits on American tanks meant immediate ammunition detonation, burning crews engulfed in secondary explosions before they could respond to fire. That morning in Normandy, that certainty proved catastrophically wrong. The Sherman that survived that impact was equipped with a wet ammunition storage system, revolutionary protection that German engineers did not know existed. Double-walled storage bins filled with water surrounded the ammunition racks, innovative design that reduced ammunition fires from 62% to 18% in controlled testing. The Germans had built no equivalent system, had never conceived of the solution, would learn about it only through captured tanks that revealed American engineering secrets they had failed to anticipate. The shock of encountering a protection system they had not imagined would be the beginning of a technical awakening that extended beyond ammunition storage into comprehension of systematic American industrial philosophy that German engineering could not match. February 1943, North Africa. German forces captured intact M4 Sherman tanks during the Battle of Tunisia. The vehicles were transported northward to Kummersdorf, the Wehrmacht's primary testing and development facility, located 25 kilometers south of Berlin. The Sherman designated War Daddy II arrived at the facility in spring 1943. German engineers immediately recognized the opportunity. Here was an enemy tank, seemingly intact, available for comprehensive analysis. The technical division at Kummersdorf assembled specialists from multiple military branches to conduct exhaustive evaluation. The Sherman would be photographed, measured, disassembled, analyzed with precision that had become hallmark of German engineering. The conclusions would be recorded in official reports that would reach the highest levels of Wehrmacht command. German expectations were clear. Americans were an industrial nation but technologically inferior to German culture. American tanks had inferior armor protection, less powerful weapons, cruder design. German tanks like the Panther and Tiger represented peak automotive engineering, precision manufacturing producing vehicles of superior capability. The Sherman, by comparison, was expected to be engineering compromise vehicle built for volume production at the expense of quality. The comprehensive testing would confirm German superiority, provide detailed analysis explaining why superior German design would ultimately overcome American quantity. The first surprise came from the transmission. German tank designers had invested enormous effort developing precise transmissions using straight-cut gears that required exacting tolerances and constant maintenance. The Sherman used herringbone-cut gears, design that German engineers had dismissed as impractical for wartime production. The transmission was simpler than German equivalents, required less precision in manufacturing, needed minimal specialized training to maintain. German engineers measured every component, found tolerances looser than they would have accepted, discovered manufacturing methods that seemed crude by German standards. Yet the American transmission functioned reliably, requiring maintenance intervals measured in thousands of kilometers, while German transmissions failed within hundreds or a few thousand kilometers in combat conditions. The technical report was unsettling. The Sherman's simplicity was not product of inferior engineering but deliberate design choice. Americans had rejected precision manufacturing in favor of engineering that could be produced with loose tolerances, maintained by soldiers without specialized training, repaired in field conditions without factory-grade equipment. The Panther transmission, which German designers considered superior, required precision manufacturing that Germany's dispersed, disrupted, and increasingly damaged industrial base struggled to provide. Panther transmissions failed regularly. Replacement components often did not fit, because manufacturing tolerances varied from one transmission to another. The Sherman's simpler design actually provided superior reliability through different engineering philosophy entirely. The herringbone gears represented decision made years before the war, rooted in American automotive industry, that had perfected mass production techniques through decades of civilian automobile manufacturing. Chrysler and Ford and General Motors had developed herringbone transmission systems in the 1930s, produced them in quantities that made the manufacturing method economical, despite complexity of production setup. American manufacturers could amortize the cost of tooling across millions of units. German industry worked differently. Production runs were limited, precision manufacturing was valued, setup costs were recouped across smaller volumes. American design assumed unlimited production. German design assumed limited volumes where precision was economical. The water jackets surrounding ammunition storage racks were second major discovery that shocked German engineers. They found no equivalent system in German tanks. The Panther stored ammunition in multiple locations, some turret racks, some in sponsons along hull sides, some below the floor. The placement had evolved through experience. Penetrating rounds that hit ammunition generally caused spectacular fires, burning crew alive or preventing escape. The German answer was armor, thickening protection to prevent penetration. The American answer was different. When rounds did penetrate, water jackets would surround ammunition, absorb blast energy, prevent propellant ignition. The concept originated from observation of actual combat performance. Army Ordnance Department had compiled statistics showing that Sherman tanks hit by enemy fire experienced ammunition fires 62% of the time. German tanks averaged 15%. The disparity was not random. German tanks stored ammunition in limited space, protected by thick armor that concentrated what space existed in less exposed locations. Sherman armor was thinner, ammunition storage was distributed, ammunition compartments were more vulnerable to penetration. American engineers recognized this vulnerability. Rather than redesigning the entire tank to improve armor protection, they developed the water jacket system, surrounding ammunition with moisture that would absorb energy and prevent detonation. Testing at Aberdeen Proving Ground had demonstrated dramatic results. When engineers exposed Sherman hulls with water-jacketed ammunition racks to direct fire from captured German anti-tank guns, ammunition fires dropped from 62% to 18%. The reduction was not perfect. Penetrating rounds still sometimes ignited ammunition despite water protection, but the improvement was revolutionary. Hundreds of American lives would be saved by the system. Hundreds of tanks would survive hits that would have meant burning coffins with previous ammunition storage arrangements. German engineers tested captured Shermans with water-jacketed ammunition storage and found the system functionally effective. The water absorbed some blast energy, created multiple compartments that isolated fires, prevented propagation from one ammunition section to another. The report noted that water-surrounded ammunition racks were a protection measure worthy of serious consideration. However, implementing such a system in German tanks would require extensive modifications. Existing designs would need to be reconfigured. Production would be interrupted. Manufacturing complexity would increase. The recommendations were noted but not acted upon. Germany's tank production was already disrupted by bombing, dispersed across multiple facilities struggling with resource scarcity. Implementing radical new ammunition storage systems would further strain a system that was already near collapse. Albert Speer, Hitler's Minister of Armaments, attended a demonstration at Hillersleben, testing grounds in June 1943 where War Daddy II was compared directly with a Panther tank. The Sherman proved superior in several unexpected categories. The vehicle climbed slopes more reliably than Panther. The transmission functioned with fewer failures. The engine, a Chrysler aircraft engine modified for tank use, ran cooler and more reliably than Panther's Maybach power plant. The Panther had superior firepower and armor, but the American tank demonstrated reliability advantages that German designers found troubling. The demonstration concluded with photographs showing the Panther succeeding where the Sherman failed on a steep climb, images that were immediately incorporated into German propaganda, praising superiority of German design. What the photographs did not show was Sherman's average reliability compared to Panther failures, the systematic disadvantage German tanks suffered through transmission breakdowns, fuel pump failures, overheating engines. The technical reports from Kummersdorf reached German high command with conclusions that were dismissed or ignored. The Sherman was declared inferior tank technically, but acknowledged as adequate for American needs. The water ammunition storage system was noted as interesting innovation, but not immediately adopted. The emphasis on manufacturing reliability rather than design perfection was observed but not acted upon. German leadership convinced themselves that German technical superiority would overcome American quantity. The comprehensive analysis conducted at Kummersdorf suggested something different. American industrial philosophy had created a vehicle that was perhaps technically less impressive, but functionally more effective, because it could be produced, maintained, and repaired in quantities and conditions that German tanks could not match. July 1943. Tunisia. The Germans captured War Daddy II, M4A1 Sherman, registered as Versuchsfahrzeug 259 with identification number USA 367641. The tank arrived at Kummersdorf. In early summer 1943, German engineers immediately began systematic analysis. The transmission was the first component removed for detailed examination. The herringbone gears were photographed, measured, compared microscopically with German equivalents. The engineering was acknowledged as competent, the manufacturing as adequate for American purposes. The next surprise was the ammunition storage arrangement. The water jackets were visible immediately. The concept was clear. The effectiveness was measurable. German engineers recognized that American engineers had solved problem differently than German approach, had accepted vulnerability in one area, armor thickness, while compensating through protective systems in other area, ammunition storage arrangement. The welding caught attention of metallurgists. American welding techniques were different from German methods. German welding emphasized precision, used techniques that maximized strength of weld joints. American welding was more crude, using methods that were adequate rather than optimal. Yet the Sherman's hull was held together by welding that had withstood combat conditions, that had survived hits that should have split seams, that had held up to thousands of kilometers of operational use. German engineers found no catastrophic failures in American welding, no hidden weaknesses that suggested structural integrity was compromised. The technique worked, though it violated German standards for manufacturing precision. The philosophy was emerging. American engineering achieved adequate results through less precise manufacturing and subsequent durability through simplicity and over-specification in some areas, under-specification in others. The engine was next focus of detailed analysis. The Chrysler A57 multi-bank radial aircraft engine had been modified for tank use. German Maybach engines were diesel, more fuel-efficient but more complicated. The American engine was simpler, more robust, adequate for tank requirements. Fuel consumption was comparable despite rumors of American engines running on less efficient gasoline. The engine ran cooler, lasted longer without major overhauls, could be maintained by mechanics trained in basic procedures, without requiring specialized expertise. The power output was adequate, not maximum, matched to transmission and drivetrain in balanced manner, that provided good operational characteristics without demanding precision maintenance. By September 1943, German evaluation was complete. The comprehensive report concluded that the Sherman was an adequate vehicle for American military purposes. The tank was not technically superior to German designs. It lacked the firepower of the Tiger or Panther. The armor was thinner than German heavy tanks, but the reliability was remarkable. The transmission operated for thousands of kilometers while German transmissions failed regularly. The engine ran without the constant maintenance German power plants required. The ammunition storage system was an innovative protection measure that German designs had not incorporated. The overall design philosophy was fundamentally different from German approach. Americans had optimized for production and maintenance rather than technical perfection. October 1943. The report was filed with German High Command. The conclusion was clear but not acted upon. German leadership interpreted the findings as confirmation that German technical superiority would ultimately triumph over American quantity. The Sherman was declared good but not great, adequate vehicle for American purposes but not cause for concern regarding German capability. The reality was different. The Sherman had been designed with assumptions that American industry could produce tanks in unlimited quantity, that any individual tank lost in combat would be quickly replaced, that maintenance and repair would occur in field conditions by soldiers with limited training. that the vehicle needed to operate reliably across vast logistical networks spanning continents. The design succeeded in all those objectives. German tanks were designed differently. They assumed precision manufacturing was possible, that skilled mechanics would maintain vehicles, that extensive repair facilities would support combat operations, that Germany's industrial base could sustain production despite any losses or disruptions. By 1943, those assumptions were already becoming invalid. American bombing was disrupting German aircraft production and targeting German industry generally. Fuel supplies were becoming constrained. Skilled workers were being drafted into military service. The circumstances that had allowed German precision manufacturing were disappearing while American ability to produce in vast quantity was accelerating. The wet ammunition storage system captured German engineering imagination most profoundly. Officers who examined War Daddy Siku recognized that Americans had invented protective system that Germans had not conceived of. The concept was simple. Surround ammunition with water. Water would absorb blast energy and prevent propellant detonation. German engineers had focused on armor thickness, on outgunning opponents, on technical superiority. American engineers had focused on solving practical problems through available means. The water jacket solution was pragmatic, effective, implementable with existing technology. German armor designers considered such systems impractical, viewed them as admission that German tanks could be penetrated and therefore need protection beyond armor itself. The psychological impact on German engineers was significant. They had been told that American vehicles were crude, inferior, designed for quantity over quality. Examination of War Daddy 2 proved something different. American design was different but not inferior. American manufacturing was looser but effective. American engineering addressed problems Germans had not considered. The comprehensive evaluation demonstrated American industrial capacity operating under different philosophy entirely than German industry. The implications were unsettling, but largely ignored by leadership more committed to ideology than technical reality. By 1944, the implications of the Kummersdorf evaluation were becoming obvious in combat. Sherman tanks in Normandy equipped with water-jacketed ammunition storage survived hits that would have meant catastrophic fires with earlier models. Panther and Tiger tanks continued experiencing transmission breakdowns that kept them out of action for extended periods. American production continued accelerating, while German production was disrupted by bombing. The German army was receiving fewer replacement tanks while being forced to field damaged vehicles kept in service by constant repairs. American forces received fresh vehicles and could discard damaged ones without concern for replacement. June 1944, D-Day. The Shermans landed in Normandy equipped with wet stowage ammunition systems that had evolved from combat experience and technical analysis. They carried 76mm guns that offered improved anti-tank capability compared to earlier 75mm models. The ammunition storage system protected crews against fires that had killed so many American soldiers in earlier campaigns. The reliability of transmission and engine meant that tanks could operate continuously without mechanical breakdowns that plagued German armor. The numerical advantage, Americans landing with hundreds of tanks while Germans could commit dozens, combined with technical improvements, meant German tank forces were overmatched despite individual tank superiority. In firepower and armor, the German engineers, who had evaluated War Daddy 2, recognized what was happening in Normandy. The Sherman tank had limitations but possessed systematic advantages that German tanks did not have. The wet stowage system meant ammunition fires were less likely. The reliable transmission meant fewer mechanical failures. The simplicity of design meant more vehicles could be produced and maintained with available resources. The American approach emphasized numerical superiority, reinforced by reliability and ease of maintenance. German tanks were technically more impressive but operationally disadvantaged because every mechanical failure meant fewer tanks available, while replacement production could not keep up with losses. July 1944, German armor commander examining reports from Normandy recognized patterns that had been evident in Kummersdorf tests. Sherman tanks were surviving hits that would have destroyed Panthers or Tigers. Wet stowage was preventing ammunition fires. Herringbone transmissions were functioning reliably under combat stress. The numerical disadvantage was overwhelming. Americans were landing hundreds of Shermans monthly while German production struggled to produce dozens of Panthers and Tigers. The combination of American quantity and technical improvements was proving decisive. The wet stowage system had evolved from observation of combat losses in North Africa and Sicily, from technical evaluation at Aberdeen Proving Ground, from engineering decisions to accept armor vulnerability, while compensating through ammunition protection systems. The symbolic representation of the wet ammunition storage system was not visible externally, but was profoundly significant internally. Double-walled racks surrounding ammunition meant that every round was surrounded by water that would absorb energy and prevent detonation. The system added weight and complexity, but reduced fire risk dramatically. American designers accepted that German shells would penetrate armor. The Sherman's protection was inferior and could not be upgraded without compromising other characteristics, like speed and crew survivability. Rather than attempt perfect armor protection that could not be achieved, they designed systems that would protect ammunition even when rounds penetrated the hull. The philosophy was pragmatic. Assume penetration will happen. Design for survival when it does. German engineers had emphasized armor thickness and firepower. Every ton of resources went into making tanks harder to penetrate and giving them more powerful guns. American engineers had emphasized reliability and ammunition protection. Every manufacturing decision was made considering how vehicle could be produced in quantity, maintained by minimally trained personnel, repaired in field conditions. The philosophies led to different vehicle designs. German tanks were impressive technically, but difficult to maintain and required resources for replacement that Germany could not sustain. American tanks were less impressive individually, but collectively more effective because they could be produced, maintained and repaired by industrial systems operating with efficiency Germans could not match. By 1945, the result was obvious. American tank production had continued throughout war at rates that exceeded German production by orders of magnitude. American tanks equipped with evolved wet stowage ammunition systems, improved engines, and reliable transmissions were everywhere, while German tanks were becoming rarer. The Panther and Tiger impressed with firepower and armor, but mechanical failures kept them immobilized more often than combat kept them disabled. American logistics flowed continuously, replacing damaged vehicles, providing ammunition, supplying fuel, supporting operations at scale that German system could not approach. The Sherman had proven adequate for American purposes. The thousands of Shermans produced were militarily decisive despite individual tank inferiority compared to German heavy tanks. The wet ammunition storage system that German engineers discovered in captured Shermans represented American engineering. Philosophy made physical. The system was not perfect. Direct hits to ammunition still caused fires sometimes, but the improvement was dramatic. Ammunition fires fell from 62% to 18% of penetrations. American tank crews that survived penetrating hits owed lives to engineers who had designed protection systems that Germans had not conceived of. The system added 900 pounds to the tank, but this weight was justified by increased survivability. American philosophy accepted weight penalty for improved protection and reliability. German philosophy emphasized performance over protection, precision over producibility. The discovery of the wet ammunition storage system was shock that revealed deeper truths about American engineering. The system was simple but effective. It used available materials, water, for protective purposes. It accepted that armor would sometimes be penetrated and prepared for that eventuality, rather than attempting impossible perfection. The philosophical difference between German and American engineering became clear through the water-filled racks that surrounded ammunition in American tanks. Germans focused on preventing penetrations. Americans focused on surviving penetrations that they acknowledged would occur. Both approaches had merit, but in industrial war at the scale World War II was fought, American philosophy proved more effective. German commanders studying the Kummersdorf reports and then observing combat in Normandy faced uncomfortable recognition. The Sherman tanks they were facing were equipped with protective systems they had not anticipated, armed with improved guns, protected by reliability that kept them fighting while German tanks were immobilized by mechanical failures. The wet stowage system was just one advantage, but it represented larger pattern. American industry was producing vehicles that functioned reliably, could be maintained in field conditions, and were protected by systems that Germans had not designed into their tanks. The combination of American numerical superiority and technical improvements meant German armor forces were facing enemies that were not superior individually, but collectively devastating through combined advantages of quantity, reliability, and thoughtful engineering. The water surrounding ammunition in Sherman tanks became symbol of American pragmatism in engineering. The system was not elegant, not sophisticated, not representative of peak technical achievement. It was an effective solution to practical problem, implemented with available materials and manufacturing methods that could be sustained across thousands of tanks. German engineers examining captured Shermans recognized that Americans had solved problem differently than German approach, had achieved results comparable to German methods through entirely different engineering philosophy. The recognition came too late. By the time German high command understood the implications, American tank production was overwhelming German defenses, and American reliability was proving superiority over German technical achievement. The captured Sherman at Kummersdorf had revealed secrets that German military leadership had failed to comprehend fully. The tank was adequate for American purposes, reliable beyond German expectations, protected by systems that Germans had not designed, produced in quantities that German industry could never match. The comprehensive technical evaluation, conducted by German engineers, was thorough and professional, but ultimately meaningless because leadership refused to recognize that American industrial philosophy had created a vehicle that was collectively devastating despite individual technical inferiority. The water-jacketed ammunition racks surrounding American tank rounds became an enduring symbol of how pragmatism, reliability, and industrial capacity could prove more decisive than technical perfection unsupported by manufacturing capability and logistical sustainability. The Sherman tank that German engineers captured in Normandy, or perhaps examined after the battle, was equipped with wet ammunition storage that had been refined through years of combat experience and technical testing. The water jackets surrounded ammunition racks, protective systems that German tanks had not incorporated. The discovery shocked German engineers because it represented safety feature they had not conceived of, engineering solution they had dismissed as impractical. The implications extended beyond ammunition protection to recognition that American industrial philosophy emphasized reliability and maintainability over precision and performance. In total industrial war, American philosophy proved more effective than German approach despite German tanks being individually more impressive. The wet ammunition storage system was concrete manifestation of that difference. Water filling the space between steel and explosives, absorbing energy when penetrating rounds reached ammunition compartments, saving lives because American engineers had designed for survival of combat damage rather than prevention of penetration.